So, hello, and thank you for coming to the talk, especially given that it's the first morning slot, and I know for sure that most of us aren't morning types. So, my name is Bojan, and today I'm going to be talking about hardware-accelerated program tracing on FreeBSD. So, before we dive into the talk, I'd just like to briefly introduce myself. So I'm a FreeBSD source committer from Zagreb, Croatia. Also a software engineer by trade, currently employed at Clara. I have been a FreeBSD user since 2021, 2022, and got my commit bit in 2024. You will usually find me tinkering with something in Beehive or the VM subsystem, but today I'm going to talk to you about something entirely different. So talk to you about some recent work that we've been doing on adding support for tracing devices in FreeBSD. So this talk is going to be split into three major sections. So first off, I'm going to introduce hardware-accelerated tracing technologies in general, explain what they do, how they fit in with other tools, and what some of their use cases might be. I'm then going to move on to the actual implementation that we did for managing, interacting, and decoding traces generated by hardware tracing the devices in FreeBSD. And the last section is going to be a case study of adding support for a specific hardware tracing technology to the newly written hardware tracing framework. So this talk is going to essentially be yet another talk about a new observability tool that's been recently added to FreeBSD and that we can leverage for advanced performance analysis and advanced debugging. So before I explain what this technology does, I will take some time to explain how this fits in with other observability tools that we already have. So, as you're probably aware, we have a whole array of observability tools available in the source tree, ranging from simple tools that specialize in giving relatively straightforward answers to queries for specific subsystems. So things like PS, procstat, fstat, the list goes on. Those are great if you want to, just find out what's going on at a high level in a specific subsystem. But eventually, you might end up needing something more flexible, something that's able to answer questions about arbitrary parts of the system, which is where software-based tracing systems often come in. So systems like dtrace, eBPF are extremely flexible, are extremely useful. We all love them, we all use them. But they do have some drawbacks that don't make them a perfect fit for all use cases. So those of you who have attended EuroBSDCon in 2022, I had the wrong year in the quote, might remember attending a talk that was dealing with the performance or exploring the performance overhead of the software-based tracing technologies on FreeBSD and Linux. So Mateusz Piotrowski conducted a performance analysis of both dtrace and eBPF on Linux, and the benchmarking results found that indeed, as expected, there's a oftentimes significant performance overhead that these tools introduce. Furthermore, not all parts of the system are equally instrumentable. So instrumenting certain parts of the kernel or certain processes might lead to system instability, which is something that you don't want to see when tracing a system and trying to find out what's going on. So the other popular category of observability tools that you often reach for are sampling profiles. So, which often includes things like performance monitoring counters. These are great for giving you a thorough statistical overview of what your program is doing during its lifetime, and providing information about how many events, the certain microarchitectural events the program triggered. So for instance, how many times there was a last level cache miss, things like that. But these tools still don't give you a good overview of what's happening at the instruction level granularity, right? So this is where hardware tracing technologies come in. Hardware tracing devices are designed to collect detailed information about the execution of your software on a given CPU core, and output that information into DRAM using a highly compressed format. So the main advantage of this is that now you have a complete overview of let's say a given function snippet or just a given program. You can find out exactly which functions were taken, which branches were taken. You often have timing information available, which makes these technologies really powerful in debugging, let's say, latency issues and things like that. So we'll move on to some other cases a bit further on. So the advantage of this being implemented in hardware obviously means that you have low overhead when generating these traces. And the other big benefit is you don't have to instrument anything. You just kick the device, it starts tracing, doing its thing. Once you're satisfied with the data you collected, you just stop it and analyze the data offline. So of course, there are downsides. Yeah. First off, these devices are not ubiquitous. They're not present on every platform. The most widespread of these technologies is the Intel's processor trace technology, yet it's been available for 10-ish years. ARM systems have some tracing technologies built in, but as I said, that's about it. The other, possibly the biggest downside, is that this tracing generates a lot of data. So we're talking about magnitude, several hundred megabytes a second if you're tracing some program that generates a lot of microarchitectural events. So you oftentimes end up having to sift through very large decoder traces, or you just have to focus on a certain snippet of the system and analyze that. So as I mentioned, some of the use cases that this technology handles very well is debugging latency issues in short-lived, latency issues in general, but especially in short-lived pieces of code. So hardware tracing technologies can generate information about wall clock time, about the cycles cycles elapsed between different packets. So you can use this to find out what's going on in a very short snippet of code, which is necessary if you're building any sort of high-performance application. Right? These traces also make debugging easier because now, in addition, so if you run a program, it crashes, and you have tracing enabled. Now, in addition to the core dump, you have a complete trace of control flow that led up to the crash. So more useful info to find out what's going on behind the scenes. Right? And a somewhat unorthodox, more research-oriented application is real-time security analysis. So several researchers took advantage of the fact that they can generate very precise execution traces with low overhead and used several tracing technologies to enforce certain mitigations or security policies. For instance, one of the more notable papers is the one that's quoted here. These researchers used Intel's processor trace technology to implement a mitigation scheme for guarding against code reuse attacks. So now we can switch on to the FreeBSD side of things. So as I said, this is a fairly recent effort. And this whole system was implemented in two parts. So the first part is the in-kernel memory, in-kernel hardware tracing framework that interacts with specific platform-specific tracing devices, manages and creates tracing sessions, does all sorts of wonderful things, but we'll get into that more later. And the other part is the actual user space tool that will start tracing for a given process, collect the data, and decode those traces into something more human-friendly, human-friendly output. So the framework itself is an event-driven framework, meaning that the framework ingests certain events from certain parts of the kernel and forwards those events back to user space so the decoder can function properly, pick up the data, decode it, and so on. It was originally authored by Ruslan Bukin, as a part of his effort to add support for the ARM core side tracing device, obviously on ARM. It was since extended to support other tracing technologies, and it allows end users to trace arbitrary processes, the ones that they can start on, to be specific, and to trace basically any piece of code that's running in kernel space. So these technologies are, in random order. ARM's core side tracing technology, which is a separate device. ARM's statistical profiling extensions. This work was done by Zachary Leaf from ARM, and the Intel processor trace backend, which was bestowed upon me. So I'll briefly touch upon the tool part, the user space part here. So the HWT8 tool is used to create processes or attach to an existing process, interact with the hardware tracing framework to start generating a execution trace for these processes, and then collect the data and decode it into a human-friendly output. So the tool can run in two modes. The first one being thread mode, which is synonymous with user space process tracing. But in this mode, when you launch a process, every thread that's spawned by this process gets its own execution trace generated, so you can decode practically everything that's been going on. CPU mode is basically shorthand for tracing the kernel. You could theoretically do that for any piece of code that's running in kernel mode, but for practical reasons, we limit this only to filtered selective tracing of certain functions within the kernel. So yeah, I previously mentioned that these technologies generate a lot of data. So fortunately, we do have ways that you can filter these or just zoom in on a specific part of the code. So the -f flag allows you to specify a arbitrary symbol name, and provided that it exists in the target executable, the tracing hardware will only generate the execution trace for that specific address range. You can do the same for executable images. So for instance, you're tracing a program and you want to see what it's doing in libc, for instance. You can filter the entire trace just to output things related to libc. And you can also prune, filter things by individual, so just inspecting a log for a certain thread. So I mentioned that the tool also does the decoding of certain, decodes the traces into certain human-friendly information types. So we do have a way of letting the user provide its, basically the output columns that they want to see decoded. Some of these, so similar to how you'd use, I think, the -O flag in the PS utility. So notable column outputs include, obviously, having a way of associating the current instruction pointer that generated the trace with its corresponding ELF symbol. Obviously doing the same for the executable image name, and some experimental, not yet fully committed feature is it provides you a way of disassembling the actual instruction that generated the trace. So you can get a live disassembly output as you trace. So this snippet is just here to give you a taste of how the output of this tool looks like and how the tool works in general. So this snippet just is a result of launching tracing for the uname program. The decoder will, the user space tool will start the process, fetch the incoming data, and as the data starts to trickle in, it will start decoding it and producing human-friendly output. Right? So this is kind of a high-level overview of high-level component diagram of the whole system, if you will. So on the left-hand side, we have the kernel space components. On the right-hand side, we have the user space components, or just the decoder, in essence. So the actual framework sits between platform drivers or tracing devices and the rest of the kernel. And as I said, the framework is tasked with creating, managing, and multiplexing, creating and managing tracing sessions and multiplexing access to the underlying tracing devices. It also has to ingest certain events from other parts of the kernel. in order to make sure that the decoder trace is correct and that the decoder is able to function properly. I'll get more into those events a bit later. So the decoder itself is tasked with initializing the actual tracing. Once it does do so, the HWT framework will just call in the appropriate methods in the platform driver. Once the tracing device starts doing its thing, it's going to start filling up this tracing buffer that's also mapped into the decoder's address space, right? So the decoder will then collect this tracing data and combine it with actual executable images that were responsible for generating that trace into the output that you saw in the previous snippet. So that's the high-level overview of things. So I had mentioned that we need to look out for certain events that are generated by the rest of the kernel. So these things include scheduling events, any address space layout change of the process, we have to react to those. So for scheduling events, if we're tracing a process and a thread gets switched, every time a thread of the trace process gets switched in to a certain CPU core, we obviously have to enable the tracing hardware, right? Once the thread gets kicked off the CPU core, we also have to disable it. Otherwise, we end up tracing everything that's running on that core, which is something we don't want to do, right? Every time a new thread gets created, we have to let the user space decoder know that this happened and update its internal data structure so that the decoding process can, move on as planned. M-mapping objects. So any M-mapped object might have executable code. We have to take all .txt sections into account and let the decoder pick them up from the corresponding binary so that the trace can be fully decoded in user space. And obviously, if the program executes a whole new image, the decoder has to drop everything and load in the new process. Right? So all of these tracing operations are exposed using via a character device. So /dev/hwt controls the initial steps for starting and allocating tracing sessions. And in general, the whole framework pretty much relies on two really important types of buffers. So the first one being the actual tracing buffer. So the memory region where your CPU is going to emit the tracing data or the packets. So in tracing modes, every CPU gets its own tracing buffer, every thread gets its own tracing buffer. That way, those generated traces don't mix in a single buffer, which would have been a nightmare and impossible to decode, right? And the second thing is the so-called event or record buffer. So this basically provides us a way of taking all of these events that are picked up by various hooks across the kernel and signaling the user space, basically forwarding all of these events to user space and letting the user space know that, hey, the tracing the device has generated new data starting from this offset, go, collect it, pick it up, do your thing. And yeah, obviously we've covered this. So this is just to showcase the actual structure that gets sent to user space. It's just a discriminator or tagged union, whatever term you prefer. But it nicely showcases all of the different types of records that are in the system. So practically all of these records are generated by kernel hooks. So those are the events that we have to kind of look out for when we're tracing. And this is by far the most common type of record, which is basically generated by the hardware when there's new tracing data available. So the user space can react to this, pick up new data, and decode it. So the actual tracing operations from user space are kind of summarized by this sequence diagram. So a user tool will initiate tracing sessions by signaling the character device that it wants to allocate, it wants to start a new tracing session. So under the hood, the hardware tracing framework will allocate a tracing context, create the corresponding process, or find it if it's not already there, and it will create a character device for that specific tracing session. So in this case, if we're tracing a user space process, it's session ID 0 and thread 0. At that point, the user space tool only interacts with the corresponding thread, the corresponding tracing session's character device. So doing an analytical operation with HWTI start tells the hardware tracing framework to start generating tracing logs for the corresponding session, which means that it's basically going to defer to the platform driver. So it's going to use this to configure the hardware and to kick off the tracing. And at that point, the user space tool indefinitely loops in this here call. Just basically wakes up, waits for incoming data, picks it up, and processes it. So the hardware tracing framework abstracts. So when we're talking about specific technologies within the hardware tracing framework, we usually refer to them as backends. So a backend is basically just an abstraction of a certain hardware tracing device that's basically described by this here interface. So aside from the usual, we have to actually initialize and deinitialize the hardware, make sure that the driver discovers proper support for the hardware, configure it. We also have the common operation here that basically just kicks off the hardware on a given CPU core. So, however, in certain systems, those tracing devices are built into the actual core. So you cannot just go blindly using these ones because there's no guarantee that they might be triggered on the core, on the target core. So for these backends, we have to do a relatively complex solving and dance that involves IPIs and a short but kind of complicated protocol that makes sure that all of these tracing devices only start sending data when every single core was initialized, right? And also the individual platform driver has to have a way of embedding some of its platform-specific metadata into individual thread structures, so that, it can actually pick up and continue tracing those threads as they get pulled in and out of a CPU core. And we have a similar interface in the user space tool, which is basically just an interface that lets the user space tool call into the platform-specific layer so that the platform-specific decoder can do its thing, process a buffer, so it can pick up new tracing buffers. Every time we mmap something, we have to scan the mapped object for executable code. So the decoder has to be able to pick up these things as well. And you obviously have to be able to configure the device from the tool as well. OK, so I think it's a good time to move on to a case study of the Intel processor trace technology. So I'm going to just provide a brief overview of what this is. So as expected, the Intel processor trace technology enables packetized logging of all sorts of information about software execution. So this obviously includes control flow information. So whether the last n unconditional branches were taken or not. This also was extended to include things like power management events. So every time a C state, a processor enters a C state or exits a C state, a packet is emitted into the tracing buffer. We also have fine-grained timing information. So packets containing that track wall clock time can be configured to be emitted into the tracing buffer, as well as packets that measure the cycle count that elapses between the last two packets. So you have very fine-grained timing information at your disposal. And the last kind of notable thing that this technology allows you to do is to insert packets entirely from software. So this is done through a special instruction called ptwrite, and I'll showcase that a bit later. So fortunately, this technology does provide some form of trace filtering as well. So you can configure the hardware with up to 2 specific address ranges. So the tracing hardware will only generate an execution trace whenever the target instruction pointer is within those address ranges, which makes it convenient to trace, short functions, things like that. It also allows you to filter the trace based on the current privilege level in the processor, which is nice and also a prerequisite for the whole thread mode versus user mode or mode of operation that we have in the HWTA tool. And it can also, the filtering can also be configured to, filter on, to kick in when a specific page table pointer is present in the CR3 register. So this, the generated execution traces, the generated tracing log can be used to construct a complete exact execution trace of, of basically whatever your software did on that CPU core. But it's not, the tracing log on its own is not enough because it doesn't encode information about the process's address space layout at the time, since that would be mostly redundant, and this whole technology was geared to compress data as much as possible. So the decoder has to have access to the actual binaries that generated this trace. And it's also virtualizable with a big caveat that it's present only on some very recent CPUs, which of course doesn't include my laptop here. So this is an example of a very common packet that you can see in the generated tracing stream. This is the so-called taken or not taken packet. This packet essentially encodes information about whether the last n conditional branches were taken or not. So every bit in the packet is going to be set to 1 if the nth oldest conditional branch was taken, or 0 if it wasn't. So obviously every packet is prefixed with a packet header. This one is rather short in this case, and is always followed by a stop bit, so that the actual hardware can generate more compact or longer forms of the packet, depending on when the event was emitted. So this packet also comes in a longer form. As you can see, this one encodes up to, I think, 47 last branches. And the stop bit can be actually, so if the processor keeps trace of the recent branches that were taken, and if it has to emit the event prematurely, this stop bit will actually get moved, squeezed further down the packet if it wasn't entirely filled. Okay, so I'll move on to some key implementation details of the actual driver that configures and starts tracing on the Intel PT hardware. So first off, the driver uses the xsave instruction set to basically toggle and manage everything related around the hardware, tracing hardware itself. So the xsave/xrestore functions, instructions provide us a way of managing resources. Those mostly include model-specific registers related to specific software, specific features present on the CPU. What this means for the driver itself is that we can just easily pre-configure the set of the values of the model-specific registers within a certain buffer in memory, and we can load those values in with one single instruction. So this makes it super easy to cut down on the additional bookkeeping that the driver has to do, and it also starts the tracing hardware in one atomic operation. And it also, once we're finished, the thread gets kicked off a CPU. We have to be able to save those values somewhere. So this provides a really nifty way of doing so as well. The actual device has a very flexible way of configuring the tracing buffer using the so-called table of physical addresses, or TOPA for short, mechanism. The TOPA table is essentially just a linked list of tables that the processor fills in as it uses to fill in the pre-allocated regions of the buffer. So in this case, part of what makes this technology so fast is the fact that tracing data gets written out directly to physical memory. So it bypasses the virtual memory subsystem, no caching, just asynchronously writes into physical memory and lets the user space cope with the fact that it's just doing its thing here. These TOPA table entries also provide us a way of generating interrupts when certain tracing regions get filled. So this kind of provides a synchronization point for user space and generates basically a buffer event that we have to bounce out to user space for the decoder to pick up the data and decode it. Right? So this is the layout of a single tuple table entry. The upper bits here encode the actual address of the output region. You can also configure the region to be in, the regions may come in various sizes. So these range from 4K pages up to 128 megabyte regions, which, if you're generating a lot of data, might be the thing you want to do instead of having just a bunch of 4K entries. And the last three fields here provide a way of signaling, basically modifying the CPU's behavior once it fills up those specific output regions. So if the stop bit is pulled up, the processor will simply deactivate the tracing device once the target region has been filled. Right? Just useful if you want to collect a short or just fill up the entire buffer and not collect any more data. But also, as I previously mentioned, you can configure it to schedule a performance monitoring interrupt. So this way, you can let the user space know that there's more data available. And if the last bit is pulled up, the processor will treat this as a pointer to the next table. We just load it into the corresponding model-specific registers and continue doing its thing. Right? So this is how we end up configuring the table in the driver. It doesn't quite take advantage of the flexibility of the format, but we just pre-allocate, the hardware tracing framework pre-allocates a buffer of a given size. And we basically just have one entry for every single 4K page. We tag every single 4K page with a topa int field. And last but not least, we make sure that this becomes a circular buffer by tagging the last entry with topa end and pointing it to the top of the table. So the CPU can keep on writing indefinitely. This here comment is something that I'm sure will bite me sometime in the future. It hasn't occurred yet. But ideally, you don't want to have an interrupt generated for every single 4K page that gets filled. It's like tracing. The amount of tracing data generated when you're tracing a short function is not the same, obviously, as when you're generating tracing information for the whole process, right? But currently, you don't have a way of sort of adaptively, strategically pulling up these topa int bits on specific places, which is something that we'll probably implement sometime in the future. But yeah, generating too much interrupts will also kind of defeat the whole low overhead purpose of the whole tracing, the hardware tracing devices. So once a performance monitoring interrupt does come in, we have to transform it into a buffer event, right? And bounce the event back to user space. So once we've made sure that this interrupt was indeed generated by the tracing hardware and that the tracing session is active on this core, we have to obviously switch off the hardware because we don't want to generate a trace log for this here snippet. And we basically update, create a buffer record with the last offset that the CPU has written to. And we schedule off another thread that's going to allocate the actual buffer structure and wake up the user space decoder to do its thing. And yeah, last but not least, if the tracing is still going on, if the user hasn't disabled the tracing, we have to rearm the local APEC vector entry and start the tracing again. Okay, we have reached the demo. That was slightly faster than I'd anticipated. Okay, so in this case, let me showcase how this looks like for tracing a random user space binary. So as you can see, yeah, I forgot to print out the actual columns. I have to implement that. But as you can see, we have started generating the trace after the process was kicked off. And the first column represents the actual offset into the tracing log that generated these here events. The second column is the ID of the tracing unit, if you will. So basically, whether thread 1, 0, or n generated this trace. The third column represents the offset into the respective executable image, right? And the last column is the actual instruction pointer that we captured during the trace. So at one point, I'll have to switch to a custom-built uname that has symbols enabled. That shouldn't be a problem. So at one point, I had mentioned that this is the default decoder output. So using the -0 flag, you can tweak the output as to your heart's content. So if we start tracing like this, you're just going to have the instruction pointer and the corresponding image. Right? If we do end up adding something like this, you can now see that we've started decoding the actual instructions that were involved in generating this trace. This is a slightly experimental feature. I haven't actually settled on a decoding library yet. We'll see which one fits better. But yeah, the -0 flag lets you be flexible with the output that you want to generate. So obviously, I have been truncating the output for this whole time, because if I do this, it goes on for a while, right? There are a lot of things going on. So one of the things that you might want to do is having a way of filtering the actual thing. And we can do this so it's a bit unwieldy because obviously I had to make sure that this symbol table is present here, that the debugging symbols are present. The -I flag basically triggers, as I said, triggers filtering for a specific executable image. And if you pass the -f flag, we can find out what's going on in uname's main. Not a lot. So it just ends up setting up the stack and calling, I think it's called print uname, the internal function. Fortunately, we can also trace this one. Okay, so that's ignore the broken output. That's also on my to-do list. But anyhow, you can actually zoom in on a specific snippet, see what's going on, and we will probably end up adding some form of timing-related information in the future. But yeah, this is what we have for now. And to cap things off, you can also do this for, as I said, kernel functions. So the symbol resolution is a bit broken right now, so you get all sorts of weird non-related symbols within the trace. But basically, we can zoom in on a specific CPU kernel function and see what's going on. And you can do it online as well. So we're generating a lot more data. Well, okay, so this here specific snippet, of course, the one that says CPU switch is what CPU switch was indeed doing. And once I figure out what's causing the other entries to appear in the trace, it'll be a lot cleaner as well. Okay, so there was another part of this demo that I really wanted to showcase, but unfortunately my laptop's a bit too old, so it doesn't include support for the PT-write instruction. So as I said, Intel PT lets you output a tracing buffer, a tracing packet from user space software or kernel space software as well. And this is just basically a compiler built-in intrinsic that is lowered to the PT-write instruction. So this is what it would have looked like if I had support for the hardware. So basically, any single value that you pass to the PT-write instruction is going to be emitted within the actual tracing log, which makes it super useful to, if you want to do manual instrumenting with this technology, you can. It's low overhead. if the tracing hardware isn't active at the time this instruction is executed, it's effectively a no-op. Right? It still does, decrease the instruction cache efficiency, but yeah. So I'll just briefly touch upon the work that went into adding all of this that I just showcased. So first off, when I initially joined Ruslan's efforts for adding more devices to this framework, I quickly found out that we have a lot of things missing in the x86 specific code in FreeBSD. So the problem here is that the performance monitoring counter subsystem and this driver use the same interrupt line, which makes it a bit tricky to share if you don't have support for doing so. So we had to add a way of dynamically registering NMI handlers, making sure that we can also share the interrupt line. And also we were missing some crucial Xsafe related APIs, so things like discovering whether the processor supports this Xsafe feature or not, and lots of other x86 specific things that I'm not going to get into right now. And back when I first joined, HWT only supported the core side device. Well, the core side device is a bit of an oddball here because it doesn't generate interrupts. So the user space hardware has to constantly pull the corresponding register and use up a lot of CPU in the process. So we ended up adding a whole bunch of things to the HWT framework that makes sure that interrupt-driven devices can also properly function within the framework. Right? And then there's, of course, the driver itself with its accompanying user space bits, so the backend and the decoder. Okay, so a lot of work went into this, but we're still not quite there yet. The tool does work nicely, but aside from fixing certain minor bugs, and we have a wish list of features that we want to see. So for instance, you probably noticed that I have been tracing all of these things online. So that's fine, but the decoding process is a bit slow, and it can also consume a fair chunk of your CPU. So ideally, what you want to be able to do is kick off a tracing session, save all of the related data into a single file, and analyze it afterwards offline. So we do allow users to dump a raw tracing log, but as I said, on its own, that's not enough. We have to have a way of somehow encoding the information about the process's address layout before, since that's a crucial information that the decoder needs to to properly decode the trace. On a unrelated, sort of related feature that we have encountered is the processor event-based sampling support. So when interrupt-driven performance counters do their thing, they can often suffer from what is called a performance counter skid. So basically, when the counter overflows, an interrupt gets generated, but by the time the interrupt gets delivered to the core, the function that triggered the overflow might not be the same function that is picked up by the NMI handler. Fortunately, Intel does offer a way of remedying this, and more fortunately, this is a packetized format. So these events are outputted into a specific memory region in a packetized format, and of course, they have support for being for being emitted into an Intel PT tracing buffer. And the Intel PT subsystem does have the corresponding packet definitions to go along with those. However, I haven't quite figured out the logistics of this since it does overlap with the performance counter subsystem. So that's pending. We're going to get to that eventually, but And last, of course, probably the most important thing for a observability tool, post-processing. Right? What I have shown you here is fine, but it might not be enough if you want to buckle down and analyze performance or latency issues within very specific functions or snippets of code. So we'll have to figure out to add which post-processing options we want to add a bit later on. And also we have to look if we can integrate with existing tools. So LLDB, and both LLDB and GDB have a way of combining the generated tracing log with the actual debugging session. I think one of them even offers a way of replaying the actual instructions with this. And also, I think the flame graph tool also can be coerced into generating high resolution flame graphs with this technology as well. Okay, so that's time to wrap things up. Hopefully I'm not much over time. Okay, so these are some of the notable reviews that you can look at. Come by, say hi, maybe leave a couple of comments. The actual driver has been accepted, but there's no point in landing it before these things go into the tree because they're obviously a dependency, right? So I'd like to thank everybody who helped review these patches in any way, shape, or form. So Mark J, AVG, Gallatin, more people that I'm sure I don't remember now. And a special thanks to Konstantin, who has provided invaluable feedback for the x86 specific bits and the PT driver itself. So yeah, I guess that's the end of my talk. So I'm happy to take any questions you might have. Yeah, sure. Yeah.
Excuse me.
Oh, the mic's coming. Just
Microphone.
Yeah.
Can you stop and restart tracing from a single user space thread?
You can. So by stopping and tracing from a single user space thread, do you mean the thread that does the decoding or the thread that's being traced?
The thread that is being traced.
Oh yeah, of course. That's the so it happens all of the time. The decoder can manually stop the tracing if it wishes to do so, but the trace stop/start thing occurs every time a thread gets put onto a single CPU or just kicked off during when the thread is scheduled, basically. So yeah, you can do that as well.
And can you switch context, so to speak? That means the whole buffer subsystem, that you have multiple of these for different sections of your user space code?
That's a good question and an idea for a nice feature. You cannot do that as well, unfortunately, at the time. So no, a single thread gets a single tracing buffer. So you cannot actually do filtering per thread, which is kind of a byproduct of the hardware and the way that we design certain things, but it can probably be built into the system quite easily. But yeah, good question.
Thanks.
Do you understand right that this infrastructure will collect only traces, like which instruction executed and which branches were taken or not taken?
Yeah.
But we're not getting any information about registers, about anything else?
So certain packets can carry information about registers. For instance, the PEBS packets can be configured to output a fairly detailed snapshot of the packet state that, of the microarchitectural state that actually was responsible for emitting that packet. I am not that sure about other packets. But aside from that, there's a ton of microarchitectural events that you can trace, a ton of architectural events that get emitted into the actual trace log. It's just that the tool doesn't have support for them yet. So.
But perhaps it's supposed to be called only by the PMC counters. But
Yes, exactly. But fortunately, this does have an option to be emitted into a PT tracing buffer. So it has its own PT packets, if you will. So it's fully compatible with one or the other, right?
yeah, but it's not triggered, not controlled by the PT. It should be controlled through the PMC. You need to set some sort of event in PMC.
Yeah. So you have to arm the actual counters before, right? That's one of the. But yeah, as far as detailed register information is concerned, this is the only thing I think that provides the register states themselves. Yeah. Well, if there are no more questions, thank you all for coming.